Okay, so chapter 2 is about data representation. So I'm going to start with the number. This is 321, but we have to put a qualifier on this. This is 321 in decimal, and this is the number you all know and love, or the number system you all know and love. And the way we get 321 is to specify values for each position of this number. This is the ones place, the tens place, and the hundreds place. This is something that I think in middle school and high school you get. But how did we get these? How do we get these value positions in this numbering system? Well, it turns out these are powers of 10, right? 10 to the 0 is 1. 10 to the 1 is 10. 10 squared is 100. That specifies the value of that position. And then your digits, you have 10 digits, 0 through 9, that specify the the value of this specific position. So in this case, so these are powers of 10. This makes it base 10 or decimal, which is what this prefix means, 10. And to get 321, we take the value of the digit, multiply it by the value of the position, which is 100, add it to the value of the next position times the value of the base at that location, 10 plus 1. So that's how you traditionally get 321. So the positions denote powers of 10, and the digits denote position values. So this is the position value of 3 for this power of 10, 2. All right. So this is all familiar with to people. So here's another number. It looks like this is 101 million and one. And that's correct in decimal. But this is actually 321 in binary as well, or base 2. So why should we care? Turns out computers are going to store 321 like that, not like decimal 321. And we need to, as computer scientists, be able to go back and forth between the abstract number that's being represented and the physical representation of it in hardware or in whatever thing is storing it. All right? So computers are using binary to store all of this information. And so here is that binary string again. And just like in base 10, there are positions in the binary numbering system. And each one of these differs by a power of 2. So at the rightmost, this is 1. This position is 2, 4, 8, 16, 32, 64, 128, and 256. Okay. Those are value positions. And these correspond to powers of 2, right? 2 to the 0, 2 to the first power, the second, all the way to 2 to the 8th power. And so we label this as base 2 and binary because of this base being 2. And so in order to figure out the value of this binary number, you take the position 256, you multiply it by the value of the digit, that gives you 256, plus 0, plus 64, and these are all zeros, plus 1, and you get 321. All right? So that's binary. Any questions about that? Okay. So positions denote powers of 2. Digits 0 and 1 denote position values. So you notice base 10, I needed 10 digits to represent a digit location. Base 2, I only need 2 digits, 0 or 1. All right. Have any of you played the game 2048? Okay. That's your homework if you haven't played it. Because as a computer scientist, you're going to need to know your powers of 2. Actually, in this class, and actually in the operating systems class, knowing your powers of 2, just like that, is very helpful. So, and that game in particular helps you learn your powers of 2. 2048 is the game. But yeah, try not to play it too much. But it does allow. There's a purpose for it that I think is very useful for your powers of 2. Okay. So your first activity, given what we just covered, find the decimal values of the binary numbers below, these two x and y, And then find the decimal values of their difference and their sum, and then convert that back into their binary representations. So I'll give you 5 minutes, or however long you need, I think 5, to do this exercise. Decimal values of this, decimal values of that, and then binary values of what you just calculated up there. You could do it any way you want, as long as it's the correct way, or correct. There isn't a correct way. You can, yeah. This doesn't have to be dead silent.
Us to keep it as 5 digits for
Yes.
the binary?
Yeah, on this one. 5 bits. Yeah. Yeah, it would suck to write 64 bits all in a row, which is why we're going to get to a different encoding system soon. Yeah, I didn't give you 60. This is like a 5-bit computer. So back when I was in your seats, I was doing 8-bit computers. That's how old I am. That was reasonable. You can write 8 bits in a row. 64, yeah, not gonna do that to you. Yeah. I was working on a PDP. Yeah, actually it was an 11-bit processor, but it was using 8-bit operations. So. Yeah, it was a PDP 11. I never got to see it. Yeah, it was in play. Yeah, some sort of dumb terminal. Yeah. Oh, you're familiar with these machines? Yeah. I used to work on that. All right. Yep. In the
because 0, 1, right? And so you have 5 digits on one more.
Oh, so that's so we're crossing that.
I'll get to that.
I was also counting a lot of people at the time. My mom just gave carrots as kids. Like, my kids are there, but you never have like less than 10. You always are counting somewhere between like 5 or 10%.
Last night.
And so by doing that,
Last night I watched a YouTube video.
and did you kind of get the motion down?
Explaining core memory.
And how your device functions?
The ones where they wrap it.
All right. What did people get? This is what? The first one. This is 19. 16 plus 2 plus 1. And then the second one is 9. So x minus y is 10. X plus y is 28. All right. Binary representation of x minus y is?
0, 1, 0, 0.
Yep. So this is your 16 position, your 8 position, your 4 position, your 2, and your 1. So 1, 0, 1, 0 is 8 plus 2, which is 10. X plus y is? 1, 1, 1, 0, 0. So this is 16, 8, 4. That That gives you 28, and then there's nothing in the 2 or the 1 position. All right. Yep. I'll get to that. How do you do that conversion the other way? It's not obvious. I think these examples are small enough that you're like, oh, I can set this bit, and I'll give you the algorithm. CS students, we're all about algorithms. We need that algorithm. I'll get you that algorithm. All right. But before we do that, here's another number. It looks like 141. Is that 141? Actually, this is also 321. It's 321 in hexadecimal. So, and immediately, I've been underlining these things. Hexa is sort of like 6, and then deci is 10. So this is actually 16, base 16, hexadecimal. So why are we doing hexadecimal? If you can recall the binary for 321, that is a long string. And if you have 321 in x86 64 bits, you're writing 64 bits, 64 digits, which is pretty painful. All right? So, the way we get 141, or one way, is to take your binary representation of 321, which is this 101 million, and to group them into groups of 4. There's your 1. This is your 4. 0, 1, 0, 0. Well, actually, it's 4. And then this is your other 1. Huh. They're related, aren't they? The reason they're related is because hexadecimal 16 is a power of 2. It's 2 to the 4th power, which means that's exactly 4 bits. So that's how you can take this ugly string and compactly represent it as hex 141, which is what this is. So this is 321 in decimal, and it's this in binary. All the same thing. They're all representing 321 abstractly in decimal.
Also a nice foreshadowing to the generic base translation algorithm.
Which I probably won't go through, but yes. I'll have an algorithm. 141. Okay, so we could do it the other way, though. So that's the shortcut way. So in hexadecimal, just like in binary, just like in decimal, we have these positions and values associated with these digit positions. First one is 1. Second one is 16. Third one is 256. So how did we get these? Again, we got those as powers of 16. 16 to the 0, 16 to the 1st power, 16 squared. So this is where we get base 16, or hexadecimal. And to figure out what this is in decimal, you take the value of the position, which is 1, you multiply it by the position value, which is 256, and you add it to 4 times 16, and then you add 1 to that, and that gives you 321 as well. Okay? So different way of representing 321. And these are all ways that you're going to have to sort of be able to reason about on a computer. So positions denote powers of 16. But one of the things, and it isn't evident yet, because you have base 16, you need 16 digits to represent your different values of that position, that number position. We only have 10 numbers. We got 0 through 9. So in order to represent the last 6 positions, we use letters. So binary, you only need 2, so that's why there's only 0 or 1. Decimal, you need 10 digits, so that's why we get 0 through 9. Turns out octal, you need 0 to 7. Octal is base 8, but we don't need base 8. Base 16 needs 16 digit positions. So when we run out of numbers, we start using letters. So A is 10, B is 11, C is 12, 13, 14, 15. But we're going to use those as single letters in our hexadecimal format. All right, any questions about this? Yeah. Yeah, you could do any sort of representations. Yeah, you could have other ones as well. And in fact, no, actually, not in this course, but yeah, there's other ones. Okay, so here's a mapping between all the 16 hex digits, their decimal value, and their binary representation. So this is a table that going back and forth from or between is going to be helpful for you eventually. It won't get burned in immediately, but eventually, as you're working with the machine level, you'll get this.
Just print off the chart and put it on our wall.
Yeah, I got different things pasted. Yeah, but this one, that one's initially, especially if you're navigating around your code and you want to see bit patterns, that would be a good. Yeah, I think that would be reasonable to memorize. You only have to memorize this one, right? Like 1010 and down, because these are, well, I guess.
Well, it's weird, so you wouldn't memorize patterns.
It's like, it looks like, yeah, for the ECE folks, it's like a truth table. All right, so let's figure out what OCD is. In decimal. So, given what you know about the hexadecimal values and the mapping of these letters to actual decimal values, what is the decimal for OCD? All right, so I'll give you guys, so work on this together. I'll give you a couple minutes. And I should say, on the exam, my exam are closed notes, closed book, and no electronics. This is something I would expect you to be able to do by hand without a calculator. So hopefully this is not asking too much. They'll be like, what are you telling your kids? Okay, so OCD, do I actually have the answer here? Oh, sweet. So 256, 16, and 1. So you take 16 times 12, which is the decimal value of C, 192. Add it to 13 times 1, so this is 205. Okay. Actually, that was the answer I was supposed to walk through. This was supposed to be your activity. But we'll do it in reverse. So this one is 256, 16, and 1. So this is 1 times 256, 10 times 16, 15 times 1. You add that up and you get 431. All right, hexadecimal. So now you have binary, decimal, binary, hexadecimal. Yes?
How many digits of hexadecimal are we supposed to have memorized?
All these digits.
Well, no, I mean...
Oh, over here. So I'm going to have you do reasonable. If I ask you to convert things, it's going to be, it's not going to be like 64-bit long.
It's going to be like 3 to 4, maybe?
Yeah-ish, yeah.
Maybe 5.
Yeah, in fact, it's already getting painful over here at 65,536 is the position over here. Yeah, it's already getting painful. That's why there's only 3 digits. That fourth hexadecimal. Yeah, well, yeah, like the next position. Yeah, so this would be 16 cubed. I think. No, wait. So this would be 4,000. 4096. Yeah, 4096. Sorry, the next one over is 65. Yeah, it gets high fast. All right. Okay, so we already referred to this earlier. There's got to be an algorithm for converting bases. And I'm going to give you the algorithm. And typically, the way you're going to do the conversion is to say, hey, I have a decimal number. What is its binary, or what is its hexadecimal representation? Because as you see, it's easy to go from the one base, like hex 141, to decimal. You just expand out the bases. It's much harder to go from like decimal into hexadecimal. You need a way of converting. So this is the algorithm. It's 3 steps. You find the largest power x of that base. So you're going to convert base 10 to some other base. You have to find the largest power that is less than your number, right? Because if it's bigger than your number, that's got to be 0 because your number's too small. And then you need to find the largest base digit b, where b times x is still less than your number. And it's got to be the largest base, so you can get all of that out of that number. And then you take, you subtract b times x from your number, and you repeat over and over again until you get to the very end. So I'm going to show you this in action. Here we have a decimal number, 15,213. This is in decimal. This might be the last thing I do. Last thing I do. 15,213 to base 16, which is hexadecimal. Here are the positions of hexadecimal if you expand it out. 65,536, 4,096, 256, 16, and 1. So we have 5 positions. We start with 15,213. And then we look at the largest base that's still smaller than my number. That's this one, right? This is bigger than my number. So that's the digit I'm looking for. That's the position. And then I want, so the highest base less than 213 is 4,096. And then I want the largest digit b, where b times that position, 4,096, is still less than 15,213. And for this one, it turns out that that digit is 3. So the thing you can do is fill in 3 at that position. And then you're going to take your original number, n. You're going to subtract off 3 times 4,096, which is, because you already took that away by putting that 3 there. So this is what's left over. And when you get this left over, it's 2925. Okay? So then you repeat. You go again, and you look for the highest base less than 2,925. And of course, it's the next one over, and it'll be the next one over going down. And then you want the largest value b, where b times 256 is still less than 2925. Turns out this is 11. Decimal 11, or in this case, you're converting into hex. So you want the letter b. So that's where this one is. That gives you the b. And you take 2925, you subtract 11 times 256, you get 109. And you repeat for base 6, or for the 16 position. Highest base is 16, that's still less than 109. The largest value b is 6. 109, this is 96, so 109 minus 96 is 13. So this position here is 6. What's left over is 13, and of course that goes in the ones position. So decimal 13 is hexadecimal D. So this ends up as capital as D. So this is your hexadecimal representation for 15,213. All right.
So do we use the division from the largest b?
Yeah, the largest b. So yeah, to find that, you would take 2925 and divide it by 256, and it would give you 11 point something something. Even though, yeah, and 11 is your answer. So someone asked before about the 0x. So if you wanted to use 15,213 in decimal in your program, you just write 15,213. If you wanted it to be in hex, then if you want to represent 15,213 in hexadecimal in your C program, then you write 0x 3b 6d, and then compiler knows that that's got to be treated as a hexadecimal constant. And then you'll see in the bit patterns that that bit pattern will show up in your debugger if you're poking at it. Okay. All right, and I went through this shortcut before. If you want to go from base 2 to hex, you just group the bits in 4 and then list out. So here's the bit pattern of 15,213. This is binary. And then you would group the bits in groups of 4 to get the hexadecimal. Okay. Do this as practice. Actually, do I have time? Yeah. Yeah, so the rest of the class, do this as practice, and then we can get the answers, and then you can go. I know you guys are probably still working on this, but I didn't want to leave without having you have some answers. So the first one, what did people get? You got 311. Is that what everyone else got? 365. I got 183 as well. Okay, so 183. So those who got the other ones, go back. These are the positions. I put these bases here. So it's 128 plus 32 plus 16 plus 4 plus 2 plus 1. All right, the next one, what did people get? I hear a D9. All right, that's what I got. Just because I got it doesn't mean it's right, though. So I was hoping to have shouts of validation. D9? D9, all right. I'm trusting the crowd here. So 2AE in binary. Well, this one I'll do. 0, 0, 1, 0. 1, 0, 1, 0. 1, 1, 1, 0. Okay. Hex 1, 3E. This I got 318. 318? 318. 150 in binary. This I got 1, 0, 0, 1, 0, 1, 1, 0. All right. And then the last one, 301 in base 16, I got 1, 2D. Is that? Yes? Okay. I'm going to assume these are the correct answers, but definitely correct me if I am wrong on the forum or the Slack channel.
All right.